So let's take a little look-see. Oh, that's not my class. Okay. We can use exponential equations to model exponential growth or decay using the basic form y equals a times b to the x, where a is the initial value, b is the growth rate, and t is the growth period. Let's take a look at this. Here's the idea. I want to define this in two terms. We would call a the coefficient, right? In terms of expressing this as a power, we would call a the coefficient, we would call b the base, and then we would have to call this whole thing here, x over t, the exponent. So that's one way to look at this, but I want to present it to you a different way, which is I think in math, it's always better to have a sense of what an equation is telling us. And so what this equation tells us is this. It says start with this. And then what are we doing? We're multiplying. So what we'd say is now multiply it by this. And interestingly, we have no variables yet. These are called parameters. In an exponential equation, these are going to be set values. Does that make sense? These are both, and so is t. A, b, and t are all parameters, not variables. A parameter means that it's going to be set in the equation and not change. So these are parameters. And the parameters of an equation are set and don't change. They're not variables. The only two variables are the y and the x, so in this case, the f of x and the x. In other words, in our bacterial example, and we're going to look here, I'm going to say, does everyone remember that bacteria example? Which was 100 bacteria, right? Double every day. If we use that as our example, then we would say the population of bacteria is a function of x such that, what number would I put? What number would I say we're starting with? We'd start with 100, right? And then, what are we multiplying by?
Number 2.
2. Why 2?
That's doubling, and then
yeah. So 100 bacteria, double. So you always have to remember, what are we multiplying by? Well, in this case, we're multiplying by, why did I use green when I clearly used purple? Je ne sais pas aussi, mais je pense ça c'est parce que je suis très stupide. So, we start with 100 bacteria, and we double, and then what does the thing say? Well, it says double every day, right? So x would mean just do this over and over again, right? But then there's this last thing. What does the divide by t of it mean? So the x of it means that we're going to double by this over and over again, right? So we're going to multiply, we'll take 100 and we're going to multiply it by 2, and we're just going to do that over and over again. If I wanted to double it 12 times, I would just set x equal to 12, right? And then it would double and double and double 12 times. If I wanted to double it 50 times, I would set x equal to 50. So what then is the divided by t doing? What does that provide for me? Why have I included that as a term? Divided by t is the period of time, the period required to do the multiplying. Does that make sense? So I want to modify our bacterium thing. Why don't we say instead of doubling every day, what if we made it double every, every 3 days? Does that make sense? What if it didn't take 1 day to double? What if it took 3 days to double? Does that make sense? Well, now, if x is how many days, do I want it to double on the first day? No, because it's supposed to take how many days to double? 3. Does that make sense? Do I want to double on the second day? No. I want it to double for the first time when x equals 3. And then when would I want to double for the second time? When x equals 6. When would I want the bacteria to double for the third time? So what could I just do with x if I wanted to make sure it didn't double until x equals 3, and that doubled for a second time when x equaled 6, and it doubled for a third time when x equaled 9? I could divide it by 3. By dividing it by 3, what I'm saying is, start with 100 bacteria, double, and then this says it takes x equals 3 days for doubling to occur. If I wanted to make it so that it took 11 days, I'd do 2 to the exponent x over 11. Does that make sense? We can just shape this formula to do what we want it to do. And if I wanted doubling to only take half a day, I could divide it by 0.5. Does that make sense? Whatever we want to be the doubling period, we can define with our equation here. This isn't how they teach you exponential functions in the textbook. I'm taking a little detour here. Tomorrow we'll look at how they teach it in the textbook, and we'll make sure we know that, so that if you get to future classes and they ask it like that. And it doesn't disagree with this. It's just a different way of thinking about it. But to me, with this, anytime you come across something exponential in life, you can just talk your way through it. This is taking a math skill and I think making it a really practical skill. Does that make sense? Because anything that doubles or triples or cuts in half, you can just approach it like this. What are we starting with? What are we multiplying by? And then to the exponent x, but we're going to divide that by how long it takes for that multiplication to happen. Does that feel okay? Okay. Can we look at an example? Exempli gratia. The number of individual bacteria in a colony starts with 125 cells. If it doubles every 3 hours, how many bacteria will be present in the culture after 5.5 hours? Can we try this one together and then do the future questions individually? Okay. So what I want to do is define a function. So let's define, and what do we want to call a function? Do we want to just call it f, or do we want p for population, b for bacteria, n for number? What do we want? C for culture?
Yes.
Okay, all right, C it is. C at x is the size of the culture. Do we want to use x for the variable, or do we want, because it's hours, right? So do we want to use h for hours? Should we say C at h? Okay, like as in different letter, or just do a better C? Is that still? Okay, let's do P. Okay, let's define P at H as the size of the population.
I did X.
That's okay. It does not matter. As long as, and you're smart enough to follow along. As long as you keep using X, you're fine. After H hours. Okay. So we would let H be the number of hours. We would let P at H be the size of the colony. If this were back in 1998, we would say let H equal the number of hours. And we wouldn't even say equals. We'd say B, let X be the number of hours. And let P at H be the population of bacteria. You don't have to write that, but that's how we used to write it. Feels good. Let statements. You still use a lot of let statements in coding. Especially if you do JavaScript coding or Python coding, they don't use let in Python, but they use let in Java. They use let in C# and C++. Anyway, okay, so now how would we define our function? Well, the population, we just look up here, and all we need to know is what's it start at, what's it being multiplied by, how long does that take? Right, so I'm just going to write that here as a reminder. Y equals A, B to the X over T. And I use T specifically because we often think of that as time. So let's get going. A is the starting amount. What are we starting at with this bacterial colony?
125.
Yeah, we're starting with 125 cells. That is our starting value. That's what we want to multiply by, right? We're starting with 125, and that's going to, because we know how bacteria divide if you've taken science, they divide by splitting in half, right? And if they divide by splitting in half, then every 1 bacteria turns into 2, which means every 125 will turn into 250, and every 250 will turn into 500, and so on and so forth. Which means the multiplier is what?
You multiply that by 2 because it doubles.
Very good. So in this case, we're multiplying by 2 because it doubles. There's nothing special about doubling. 2 happens to be what we're multiplying by here, but it could be anything. Does that make sense? But note, this isn't a variable. It's not like this is going to change to 3 next time or change to 4. These are parameters. They're set for this equation. They're locked in. Does that make sense? Now up here, we're going to have x. But x represents hours, right? And we know that this doesn't double every hour. It doubles after every...
3 hours.
Where is it? 3 hours. So if it doubles every 3 hours, then we have to factor that in. And we have to say, we don't want to double when x equals 1. We only want to be a third of the way to doubling when x equals 1. We don't want to double when x equals 2. We only want to be 2/3 of the way to doubling when x equals 2, because x isn't going to double until the third hour. Does that make sense?
Right.
And again, there's nothing magical about 3 hours. I made those numbers up for this question. Does that make sense? I just made them up. They're made up numbers.
Hold on, can I go get a calculator?
Sure. Yeah, absolutely. Okay. Can we graph this relationship? Graphing exponential functions is kind of clumsy, right? I find it clumsy because that shape doesn't work easily, right? The easiest way, it's not like a parabola where there's a nice, neat step pattern, and it's not like a, wow, what a terrible choice of color to make that clearly the axes. There we are. And it's not like a line where you can just do rise over run, draw your second dot, and put a line between it, right? Does that make sense? So this is a case where I often find graphing pretty unhelpful. You know what I mean? Because your graphs inevitably, A, get out of control quickly, and B, are messy. But let's try this. Since we're at 125, we're probably counting by hundreds, right? That'd be 500, 1,000, 1,500, 2,000. Does that seem like a reasonable scale for the population? And then hours, you know, probably just count by ones. So that'd be 5, 10, 15, right? Where does the population start? 125, so that's like roughly there. So at 0 hours, it's 125. At 1 hour, what did we say it was? 250. At 3 hours, we said it was... It'll go from 125 to 250. 250, it'll go to...
Wait, where'd you get 250 from?
Because what are we doing? Oh, sorry, but it shouldn't be at hour 1. Sorry, it doubles every 3 hours. So at hour 3, it should go up to 250.
Hold on, how'd you get 250?
Okay, well, let's go through that. So here's our x value, which is hours, so our h value, right? And then our y value is population, right? And at 0 hours, it's 125. How long does it take to double?
3 hours.
3 hours. So at 3 hours, it'll be, what's that doubled?
250.
250. Good.
But
What's 3 more hours?
Okay, well, this kind of confuses me because I used a calculator and I typed in 125 times 2 to the power of 1 divided by 3. So I thought that's what you had to do.
Yep, that's right. And that'll give you after 1 hour. And did you probably get like 1 something?
157.
Yeah, you're totally right. I'm just not going to include it because I don't want ugly numbers, Seth. But you could totally do that.
And then I did times 3 and it doesn't even equal 250.
Yeah, try it. If you do 125 times 2 to the exponent 3 over 3, it should equal 250. So try that.
You do 3 over? Okay.
Yep, try that. Because the x value is always over 3, right? When will the next doubling happen? 6 hours, and what will it be? And then when will the next doubling come?
Hold on, slow down.
And what will it be at? 1,000. And the next doubling would be at 12, and that would bring us up to 2,000. And there's no point going after that, because how high does my graph go? 2,000.
Okay, I get it.
So 3 would be at 250. Yeah, you're good?
Yeah, I think
Great. Does anyone else need me to slow down, or are we good? Okay. Speak up if I'm going too fast. So at hour 6, we want to go up to 500. Then we said at hour 9, it should be up at 1,000. And again, what shape are we discovering? that classic, and again, it's much steeper than a typical parabola, actually. It's the exponential curve. The exponential curve. Now, we want to know what the population will be after 5.5 hours. Can we estimate that from this graph? Sure. Is it going to be perfectly accurate? No. We can estimate. And how would I estimate that from the curve? Well, I would want to go to 5.5 hours. Is that on the x-axis or the y-axis? Great. So I'd go to 5.5, and I could just follow that up until I hit my curve, right? We've all used curves to predict things, right? And then what do I do with it? Yeah, I'd follow it over, and I would follow it over to the y value. And what's that tell me? Like it's going to be somewhere between 400 and 500. Looks like it's on the higher side of. So maybe roughly 450 to 500. Do you know what I mean? Maybe 470, question mark. Is it easy to get a precise answer on a graph this way? No. So what should we use? We can use our function. And what I would do is I'd just say take our function and evaluate it where h is equal to 5.5.
Oh, well.
Yeah, that's right. And so what would I do? I'd say 125 times 2 to the exponent 5.5 divided by 3. And you can just plug that into your calculator. Right? By the way, if you wanted to, could we write that as a fraction that doesn't have a decimal in it? This, I'm going to draw this in like purple to say like you do not need to do this. All right? But that'd be 125, right? Why do I keep writing decimal places? 125 times 2 to the exponent. What's the cleanest fraction of that with no decimal? Sorry? Not 5 over 6. What would we have to do with the fraction? Double it, but that doesn't give us 5 over 6. It would give us 11 over 6, right? Does that make sense? If you double 5.5 over 3, you would get 11 over 6. Those are equivalent fractions. If we wanted to do this with power rules, we could take 2 and put it to the exponent.
I got.
We could take 2 and put it to the exponent 11. And then we could take not the square root, but the 6th root. And then we could multiply that by 125. Do we want to do that here?
No.
But if we didn't have a calculator, could we do that? Could we multiply 2 by itself 11 times? And then, you've probably never learned how to take a square root by hand. There's an algorithm called Newton's algorithm. It's a huge pain. It's an enormous pain in the butt. Be thankful that you never have to do it. This is correct, but unnecessary.
I got 445.
That makes beautiful sense.
That makes no sense.
Oh, sure it does.
Our estimate's a little off, like 5 off. Not 5 off.
Yeah, what it means is that I didn't draw my curve super accurately, which is fine, right? That's the whole point, is it's hard to draw an exponential curve accurately. So just use your calculator.
No. Because at just past 5 hours, like not even like at 5.5 hours,
Yep.
we already reached that 500 mark.
Yep.
So how the heck would we get?
Because, and this is where thinking exponentially gets really hard. Exponential functions change really, really, really fast, right? I mean, we know that because it goes from 125, and when you double, like by the time you get to 6, it's only at 500, and then by the time you get to 12, it's up at 2,000, right? The growth accelerates dramatically. But what did we end up getting when we plugged this into our calculator? That's okay. What did you get, Seth? It's confusing. It's tricky. What did you get, Seth?
445.
And was there a decimal?
Yeah, there was definitely a decimal. 449.
Great.
3591.
Great. And in math, it can be tricky to know where to do decimal places. In science, we have rules because everything's measured values. Officially, this keeps going on forever. If I ask for an exact answer, well, that would be the exact answer, right? I won't often ask for an exact answer, but if I do, you just have to keep it that way. Does that make sense? There's nothing you can really do about it. On the other hand, if I ask for a reasonable answer, or if it's a real world problem, unless I say otherwise, round to 2 decimal places at the end. Does that make sense? That's a good rule of thumb. So we would round this one to what then? 445.45.
I'm just gonna do.
Yeah.
The 5.5, where you use the x, you don't actually multiply that in the equation. The only thing that you can multiply is 5.5, where the x is.
Yeah, that's right. Where does the 5.5 go? It goes in place of the x. And everything else stays the same because everything else is a parameter, right? 125 is set. That's baked into our equation. This equation is used to talk about 125 bacteria. The times 2 of it is set. This equation is used to talk about 125 bacteria that double. The divided by 3 is set. This equation is designed to talk about 125 bacteria that double every third hour. Not every hour, not every second hour, not every fourth hour, every third hour, right? The only thing we put in is how many hours. Does that make sense? So it's got 3 parameters and 1 variable. The parameters are set. And what are the parameters? One parameter is what you start with. One parameter is what you're multiplying by. And one parameter is how long it takes to get to that multiplication. Does it happen every time? Does it happen every 5th time? Does it happen every 12th time? Does that make sense? We put 3 parameters in, then we build our equation. Once we've built our equation, now the only thing that ever changes is the x value, right? And if I wanted to know how many bacteria there'd be after 30 hours, well, that'd be trivial. In fact, on a piece of scrap, off at the size, whatever, let's just do that. How many bacteria after 32 hours? Just use the same equation. I'll remind us the equation was P at H equals 125 times 2 to the exponent x over 3. Is that right? Right, it was 125 in 3 hours? Okay, cool. So use that. And again, are you going to do these equations by hand? No. I mean, I guess you could. The numbers get real big, real quick. In fact, your calculator is probably going to spit something out at you ugly, and I want you to be smarter than your calculator. Use either standard or scientific notation, but do not use what your calculator just spits out at you as though that's an answer. Do you have a fancy pants calculator? I love that. That's nice. What would this be? This would be P. What are we subbing in? I shouldn't have put an X up there, of course. I should have put an H up there, right? But will you all forgive me for that? Great, I'm not going to change it. And what is it? 125 doubles every 3 hours, and we're going to let this run for 32 hours. Does 32 divide nicely by 3? No, right? So there's not much to be had there. Now, if I had to do this by hand, what would I have to do by hand? The exact value would be 125 times 2 to what exponent? To the exponent 32, and then we take the cube root. Does that make sense? That's the exact value. Do I want the exact value? No, because can anyone tell me off the top of their head what that number means? No, me neither. So in this case, I want just a real answer. When you plug this into your calculator, what's your calculator spit out at you? I bet it's going to be one number, decimal, a bunch of numbers, and there's going to be an E in there. Am I right? Oh, does it actually give it to you clean? What's the clean number? 203,187.33. Okay. Oh, that's not too bad. Oh, I guess we've only doubled. I'm thinking every 3 hours, right? So let's try another one. What about after 6 weeks? Has anyone taken chemistry with me yet? Does anyone know the dimensional analysis? We have 6 weeks. 6 weeks. 6 weeks. Let's make a ratio here. We don't want to talk about weeks. What do we want to talk about?
Hours.
Does anyone know how many hours are in a week? I don't. But what do I know about weeks? Okay, so I know that there's 7 days in 1 week. Hey, I've just made a ratio. Is this ratio true? Then weeks should cancel with weeks, and what will I now know? How many days? And by the way, what's 6 times 7? Divide by 1? Great. But I could keep going because I don't want days, I want mathematically, if I put hours on the top of this function, what am I going to have to do? Right now my unit would be days hours. That's not useful. How do I get rid of days? Where do I have to put in this fraction? But where? If I put on the bottom, I'll be dividing days by days, and that will cancel. Now, this fraction has to equal 1 because we don't want to change it. What's the true 1-to-1 relationship between hours and days? Yeah, 24 hours is 1 day. So this is really saying 1 divided by 1. So we haven't actually changed our numbers. 7 days divided by 1 week is just 1. So we've taken 6 weeks, multiplied it by 1, and then 24 hours divided by 1 day is also just 1. So we haven't actually changed our value, but we've changed the number because 7 days is 1 week and 24 hours is 1 day. This is called dimensional analysis, your best friend. If you take chemistry with me, boy, will I teach you dimensional analysis. You'll be great at it. You're going to soar at it. Anyway, real quick, 6 times 7 is 42. 42 times 24 is what? 4 times 2 is 8. 4 times 4 is 16. 2 times 2 is 4. 2 times 4 is 8. 8, 0, 1, 9, 1, 9. That should be 1008. I feel like I screwed up. Is it 1008? Boy, that just feels like a number that shouldn't be the real answer. Okay, now, how do I use my equation? P at H would be P at 1008, and that's going to equal what? I start with how many bacteria? 125. What am I doing to them every time? I'm multiplying them by 2 because the population is doubling. How long does it take for that to happen? 3 hours. How many hours am I doing it for? 1008. Do that. Is it too big? It's too big. Isn't that crazy to think? That population of bacteria will be so big that your calculator can't handle it. For the sake of argument, let's try something. What's 1008 divided by 3? Let's see if your calculator might like it a different way. Just do that quickly. What is it? 336? See if we can do that. See if that, your calculator might, because what your calculator might do when it does this is first go to the exponent.
Still doesn't work.
Still won't work? Let's see if Desmos can handle a number that big. And if Desmos can't, let's see if Wolfram Alpha can.
336 for the 108 or 1008 divided by 3.
So let's do P at X, or P at H equals 125 times 2 to the exponent H over 3. Hey, look, there's our function. By the way, why is it going back in time? Well, we didn't tell it not to. In our example, is there such thing as negative time? Maybe. Maybe we could figure out where the bacteria colony started, but we're not going to worry about that. And what did we want? 1008? Desmos can handle it. Scientific notation. 1.75 times 10 to the 103. 10.75, or was it 1.75? Times 10 to the exponent 103 means that this decimal actually has to move this way how many times? 103 times. I'm not going to do this, but that number would be 1753, or 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm done, but you get the idea all the way out there. Is that number pretty big? This is why we don't leave food sitting out, team. Okay. Cool. Let's try this. And again, when we talk about numbers getting big quickly, like holy crow, that number, like we're not just talking a big number, we're talking like an unfathomably, that's more than there are atoms in the universe.
No.
Yeah, oh yeah. Yeah, she's a big old number. So like, that's a big number.
There can't be more atoms in the universe than bacteria.
Well, that's right. So this couldn't actually happen.
Oh.
Right? Yeah.
What happened if you open up that? Oh, the bacteria.
They'd run out of food. Yeah, they'd run out of food and some of them would die, right? So a model is only good up to a point, right? It assumes that it just keeps happening. Okay, now let's talk about decay. Zinc 71 is radioactive. It has a half-life of 2.4 minutes, which means that every 2.4 minutes, its mass decreases by half. This is how radioactive decay works. the atoms interact with each other in such a way that in a set period of time, half of them will decay, which means the decay starts off really fast and will start to slow down. What function can be used to model the radioactive decay of zinc-71 if we start with 155 grams? Don't worry about this number 71, by the way. That's literally just the name of this stuff. If you're a chemistry student or a physics student, you know that just means it's referring to the mass of that particular zinc isotope. If you look at the periodic table, what does zinc normally weigh? Stable zinc weighs how much? Find it on the table. Yeah, 65 atomic mass units. So if we get heavy zinc, it's unstable. So heavy, unstable zinc decomposes. You don't need to know that. This is a math class, but as it happens, I'm a science teacher, so we're going to talk about it. So, how do we lay this out? How much zinc do we have? We start with 155 grams. That's right. And then what else do we know? It decreases by half.
We got to divide by 2.
So we could either divide by 2 or multiply by, absolutely could use a negative exponent, which we'll talk about that later, or we could just multiply by a fraction. Any of the above works. We could also multiply by a decimal. What's half as a decimal if you like? Okay.
Just divide it.
So here's what we're going to do. We're going to say the mass of this after time.
I did f of x.
And, yeah, which is totally fine. The mass of this given time is going to be equal to, well, what did we say we started with? 155. And then you have a million options. You could divide by 2 if you want. I'm going to suggest always multiplying. And I'm just going to say multiply it by a half. Now, that is exactly the same thing as saying divide by 2, because what does that symbol mean? Divide by, and what are we dividing by? 2. So there's an argument, by all means. Yeah, so if you prefer to write 155 divided by 2, nothing wrong with that. This I stick with just because then the format doesn't change. We're just always multiplying, but 6 of one, half dozen of the other does not matter. And then T for time, but does it decay every minute?
Nope.
No, we don't want it to have decayed yet after 1 minute. We don't even want it to have decayed yet after 2 minutes. We need to make it so that the first time this exponent actually equals 1, the t equals what? 2.4. So to do that, we need to make sure that the exponent isn't actually growing with t, it's growing with t divided by 2.4. That means that the real exponent will be 1 when t equals 2.4, which means that the first time it gets cut in half is when t equals 2.4. Does that make sense? That's why we divide in the exponent here, because we're saying it's not until this value is that value that the exponent actually equals 1. In other words, it's not until this number gets to that number that we actually either double or, in this case, divide it in half. And if you start to get the feel for that, so the way I would say this expression out loud is, we're starting with 155 grams. We're going to cut that in half, but we're not going to cut it in half until t gets to 2.4. I'm going to write that here. So we start with 155 grams. Is everyone comfortable with that W slash being with?
Yeah.
Okay. And we're always dividing in half. And takes 2.4 minutes to divide in half. So we don't want to do it every minute. We want to do it every 2.4. And I never made let statements here, but of course I could over here. I could say let t be the time in minutes. That's important, right? Because if I set time in seconds, would the equation be different? Yeah, if I set time in hours, would the equation be different? Right. And then we're going to let m at t be the grams of zinc. And maybe if that feels a little squished, you might want to just use your pen, highlight everything, and maybe just slide it around a bit. No.
Wait, I have a question. So, with the exponent, like that t is just like a placeholder, right? Like if I were to actually do the math, I would know the t is compared to the exponent.
Yeah, exactly. No, t is not to the exponent. T is in the exponent. So you'd take 155 You'd multiply it by a half, and then you'd go into the exponent, and let's do an example here. What if we wanted to evaluate this after 16 minutes?
I can answer this one.
Good, but I want you to wait a second, but I will let you answer it, I promise. Yep, so give it a try. Try it out. I have faith in you. Everyone try it out. And then Seth has got dibs on answering this one, so we're going to let Seth answer it, but we're going to let everyone try it out first. All right? We're going to use our equation.
When I give my answer,
yes, sir.
The equation, can I just say f at x?
Yep, absolutely. I'm going to write it my way, but you say what you're doing, okay?
I know you're saying m at t.
Yeah, but it doesn't matter at all.
Yeah,
you can use
easier for me to remember.
Absolutely, and you can always use any letters you like. It does not matter. If you find it helpful to use letters that reflect the word problem, do that. Some people find it much easier to always use y and x and to always use f of x. Go nuts. Both are totally appropriate.
See how she beautifully puts it into scientific notation for me?
Oh, she is beautiful. Can I see?
Yes.
Yeah, very nice. And well done. That's great. Yeah, well done.
Alright, I got my answer.
Yep. Let. Sorry. How are we doing?
Test writers that are
Send them on over.
exact run to exact.
You bet. Yeah, send them over. Actually, why don't I just come to yours?
Yeah,
That's even better. That's easier.
I don't know how many I'll need by time.
No, that's fine. I'll come right to. How's the test going?
I was great. He was just stuff in the back of my heel and I gave her a dirty look and she looked like an utter bitch. But I mean, I probably look like a bitch.
All right, Seth, my friend, what did you do?
So I started at m at 16.
Oh, look at you doing it my way too. God bless you. Equals?
I wrote it as f5.
Yeah, that's fine. You did great.
Easier. Equals to 155 divided by 2. That's just how.
Yep, that's fine. I'm happy to write that.
To the power of 16 divided by 2.4.
Great. That's awesome. I am going to change this to times a half, but not because Seth's wrong. Seth's entirely right, but just so it matches my equation. Does that make sense?
Yeah.
But what Seth wrote here was totally cool. And this is probably going to be a pretty small number already, because this is going to be cut in half roughly how many times? Like if we want to know how many times this gets cut in half, what could we do? We could just work this exponent out, right? And what's 16 divided by 2.5? It's going to be like roughly what? 6 times? More or less? 6.6? So this is going to be cut in half, cut in half, cut in half 6 times. So it's going to be pretty small, right? What do we get as an answer?
I got 1.5256856646.
Great. And was there any scientific notation in there, or was it just 1 point? 1.525. Give me a couple more.
No, 1.85.
I got 8. Hold on.
Or no, sorry, 9.854.
Oh, interesting. We're getting different answers. So let's see if we.
Oh, mine said scientific notation.
Well, but they should match. So let's make sure.
No, I got the same answer. I did.
Did you start with 125 by chance?
I started with 155.
Okay.
Multiplied by 1.
Multiplied by half to the exponent, and then 16 over 2.4. You might have to. You know what I think you have to do? I think on your calculator, look at me. I think you need to put your exponent in brackets in your calculator.
Oh.
Well, it depends on the calculator. On the yellow ones, you don't, because it puts you up in the exponent. But my suspicion is that yeah. So now look here. That gave us 1.257. And as a rule, I've said, unless I tell you otherwise, how many decimals should we just keep? 2 in the final answer, so we'll call this 1.53. Note, never round until the final answer. So what would be, therefore, there would be...
I got 1.5. I didn't get a scientific notation.
That's okay, yeah. It would give you scientific notation if it was small enough. There'd be 1.53 grams remaining.
I got 1.5 after I put it in
Have you guys ever heard of carbon dating something? Whoa.
Practice questions.
Sorry? I would date Carbon. But as you know, the first question I would ask Carbon is what the largest animal it thinks it could defeat an unarmed combat is. But have I explained to you guys that that's the perfect first date question?
No.
Next time you're on a first date, just casually ask the person, what do you think the biggest animal you could defeat in unarmed combat is?
A giraffe.
And it will tell you everything you need to know about the person you're on a date with.
A whale.
Interesting. Anyway,
We're not on a date in a math class,
Angela, I'd like you to keep it platonic here, and then sparks may fly the rest of the day, of course. But for the moment, if we could focus, I'd appreciate that. Could we graph this? This is ugly. I hate graphing exponential relationships, but sure, we could graph it.
On today's cafeteria menu, we have chicken wing soup for $2. Garden salad for $3.50, and our featured entree, which is grilled cheese with fries for $5. That's on today's cafeteria menu. Have a great day, Eagles.
Maybe I should just order pizza, but that's expensive, so I'm gonna eat fries.
Okay, so listen,
Can I do it by like 40, 80?
You can do whatever you want. These are ugly to graph, right? We know this starts at 155, so like that would be there. But then in this case, where's the first half point? Right? Like it would be 155. Oh, sorry. It'd be 0 and 155. And then when does it double for the first time? Or cut in half? 2.4. And then what's half this value? Ugly. 77.5, right? Somebody check that, but I think so. So we have to go to like 2.4 and 77.5. Okay, that's ugly. What would the next doubling time be? Team?
So let me graph this.
4.8. And what's half of that? It'd be 35 plus another 3, so 30, 38.5. So it'd be 38.75, I think. Can someone check that? Did I get it right? It's a miracle. So that'd be about there. What would the next doubling point be?
Yeah, if we got a worksheet on this, I'm going to go a lot slower than you.
Yeah, and that's okay. What's half of this? 19 and then plus 19.375? Right, I think. I wouldn't trust me. I wouldn't trust me as far as I can throw me. What did I might have screwed up. What am I adding here each time? I'm adding 2.4, right? Because that's how long it takes to double. Now I could use my equation. Did I do that right?
Yeah,
4 plus 2 is 6. 0.8 plus 0.4 is 1.2. Yeah. Okay, what would the next point be? 9.6. And what's half of this? 9 point... Somebody help me out.
Hold on.
9.6.
Yeah. And I hope what you'll see is, I think graphs of this are visually interesting, but are they a good way to get numbers? Would you trust a number here? No. So, can we graph this? Yes. Can we use the graph to estimate? It's a bad idea. Use the equation.
So if you're doing like a test on this and you had something like this and I just wrote bad idea, would you give me a passing grade?
Would I give you a passing grade? Sure. But if Critton wrote the same thing, he'd fail for sure.
Oh, that's how you're being funny.
That's right. No, I'm kidding. I'd fail you both. Even if Critton's answer was right, I'd fail you both. You heard me. Okay, guys, there's practice questions here. I want them done. And the reason they're not from the textbook is, again, tomorrow we'll learn like how the textbook introduces this stuff, which is not wrong, but I think this way is going to serve you a lot more usefully using exponential equations in your actual math life and science life.
Hold on, can I see the graph?
Yeah, you bet. This one here or the first one? Yeah, you bet. Hey, what's Friday? The note from Friday. Which was...
What would you do if you actually smacked on me?
Oh, it's not on that. I saw
Sarah.
I bring you a Dr. Pepper can tomorrow.
Mr. Orlando, I can't see you. Oh, Mr. Orlando. I can't see.
Sorry. Howdy. How you doing?
I'm staying after school tonight. I don't know if you want.
Love it. How you doing, my friend? Hey. Are you interested in helping out on Grade 8 Day for Science? Do you have any other obligations? You can play anywhere else? Does that appeal to you? Yeah, you'd be in here. You've taken science. You did 9-10, obviously, right? Do you like science? Think about it. If you're interested, I'd love to have you. I think you'd have it. Sorry?
I didn't do that.
That's okay. Didn't ask if you did well. It's not like Grade 8 Day. I'm not going to be like, now everyone, show them your report cards. No, it's like, you just strike me as having a good, calming, kind of chill personality. And I think you'd be, yeah. If that appeals to you, let me know. Let me know tomorrow. If it doesn't, that's cool too. Yeah, you get some hours for it. And yeah, we'll put you at a station where we'll do some kind of demo. And they're pretty, like, you're not even really demoing, the kids are just kind of doing stuff and you're there to make sure they don't make a mess. And if they have questions, not even about the science, who cares, but just about e-scale. Because that's what it's really about, right? It's just, it is, when is Grade 8 Day? Wednesday? Wednesday. Yeah. Let me know tomorrow what you think. Yeah. Yes. You want to help on Grade 8 Day?
I'm already doing it.
You're doing, oh, you're a tour.
I'm touring.
That's right, even better. Is your tour coming to me? I hope so.
So is that like
It'll be most of the day, yeah. So what do I need to sign you out of? What are your other classes? Okay. And are you doing fine in all those? Like, they won't give me a hard time